Hello, everyone. Welcome back. Today, we want to talk about vectors, learn what they are, and also talk about some applications of them. So our goals are to understand what the difference between scalars and vectors. We'll explain what both those terms mean. We'll learn to graph vectors, uh, and subtract them, and also find what's called the magnitude and direction, then basically build some application problems involving vectors. So let's start. So there are two essentially types of numbers we deal with in real life. So this number we're usually used to most of the time is called a scalar. Okay. A scalar is a quantity that is described only with a magnitude, only with one number. And it's called a scalar. So good examples are temperature, pressure, weight, and also I'm saying speed. So like say if I just say how fast are you driving down the highway, 60 miles an hour, that's speed. Of course, you know what the rest are: temperature, pressure, and weight. All these things only needed one number to describe them. But a vector is something we have to describe with two different numbers, at least. And that's by not only a magnitude, but also a direction. Okay, so examples of that are velocity, which is different from speed, acceleration, and force. So especially velocity and force are some of those common ones where you need vectors. So this type, we talk about velocity, we mean a magnitude and direction. This is like what they have to do when working with ships and airplanes. When we don't have highways or roads, then not only is your speed important, how fast you're going, but also the direction you're going in. Okay. So airplanes have to deal with that because they have to basically specify a speed and a direction, and the same for ships. And then force is also really important. You have to know not only how hard a force, how essentially if you're pushing something, how hard you're pushing it, but also what direction you're pushing. Those are all important. Okay. So vectors things have to be specified with two values, magnitude and direction, where scalars just need one. Now, also two vectors are equal if and only if they have the same magnitude and direction. And also the way we write vectors, so in print, in books, and other things, and here I'll use this as well, we often put vectors in bold type to distinguish them from scalars. For example, like the vector A would have like a bold A. Okay. If you write them by hand or some in books, you'll see with an arrow over the top of vector to indicate as a vector like this. So we'll arrow over A. Let's take a look over here at some examples. Okay, for example, this might be our vector A. And here I'll write it with a little arrow over it to indicate it's a vector. So its magnitude is its length, okay, how long it is. That's how we represent it. And then its direction is pointing this direction. Okay. Now, what if A was pointing the opposite direction? Well, that would actually be negative A. Okay. So imagine if I had a vector the same length as A, just pointing in the opposite direction. That's actually negative A. That's important to know. Okay. Let's have another vector B, and maybe B looks like this. Okay. Now, if you notice, B is pointing in, in fact, let's make B a bit longer. So let's say that B is the same length as A, but it's pointing in a different direction. That makes it a different vector. Okay. Even if the magnitude, even the length is the same, that makes it a different vector. Okay. Or if we have a vector C, if it's pointing maybe the same direction as B, but has a different length, that also makes it a different vector. Now, there is some relationship between them. They're pointing in the same direction, but they're different vectors. Okay. So, as we said, two vectors are equal if and only if they have the same magnitude and the same direction. Okay. So here we can say that A is not equal to negative A. Okay. And then, of course, A is not equal to B. And then, of course, uh, A is also not equal to C, and B is not equal to C. Those are all different vectors because they either have different magnitudes or directions or both. Okay. Now let's do one more vector, and so I'll do my best to try and draw it the same. This is vector D. Okay. Now what I'm trying to show, if I can, it has the same magnitude, same length as A, same direction as A. I'll say, but A is equal to vector D. Now, one thing I'll say, this can be a little confusing at times because even though the vectors are equal mathematically, in terms of having the same length, the same direction, their effect can be different. For example, this is a force. If they're both forces, then where I apply each force can certainly have a different effect. But as far as mathematically, they're equivalent. They're equal. Okay. Now, um, let's talk about the next idea, adding vectors. Probably make sure it looks like a B here, but yeah. Okay. So adding and subtracting vectors. Well, actually, let's actually take a quick look at graphing some first. I should do that first. So hang on. Let's look at graphing example or two. All right. So vectors could be, let's do a really basic grid right here. And we're not going to put a lot of detail into it because we just want to show some basic ideas. Okay. Now let's mention a couple points. Let's say now these are points. Okay. All come P. So point 1 is just the origin, 0, 0. Point 2, let's say, is 2, 3. Point 3 is, let's say, how about -2, 0. And point 4 is -3, 1. Okay. Now, let's say I have a vector I want to call vector P1, P2. And I can often write that. So basically, vector goes from point P1 to P2. Okay. So it goes from 0, 0 to 2, 3. So 1, 2, 1, 2, 3 right here. And also a few more things to talk about the vector, which I should mention. So the starting point of a vector right here is called the head of the tail of the vector. That's the end of it. And then the arrow end is called the head. So here, my tail is at the point 0, 0. We're going from, when I read this point P1 to P2, the tail is at point P1, the origin, and the tail of the head is at point P2. So here's my vector P1, P2. If I look at my other vector, let's see what a vector, let's call this one P3, P4. Then it goes from my point P3, which is -2, 0, to one point -3, 1. So this is right here. This is actually a short vector. So once again, its tail is at -2, 0. Its head is at 3, 1. So that's the vector, this vector right here. Okay. And as you can tell, those are not the same vectors. They're obviously not equal because they have different magnitudes and different lengths, or different directions and different lengths. Okay, so now let's talk about adding and subtracting vectors. So if we have two vectors like the ones we saw above, we can add those vectors, or we can also subtract them. Okay, we kind of add many combination. Of course, you can also add together as many as you want. Let's kind of explain how we want to do that. Let's say I have, once again, let's call this vector A, a vector like this, A, and I have a vector B, okay, and maybe vector B looks like this, points in that direction with that length, okay. Now, if I do A plus B, that's actually a new vector, which can have, most likely have a new direction and a new length. So the way I'm going to indicate that, so let's first off, and often if imagine this being two forces acting on a point, a common point, that's a bit too long. Imagine if these are two forces acting on a point, okay, then basically we expect that it's going to be pulled or pushed somewhere kind of this direction, okay, kind of in between the two forces. All right. Once again, this is A and B. So the way we're going to think about adding those, especially in a graphical way, is something called a parallelogram method. But basically, what we're going to do is if I take and I say this here in the reading here, so basically, if I take the tail of vector B and put it at the head of vector A, looks like that. Okay. Because once again, I can actually move this vector around. As long as I maintain its magnitude and direction, I can move it around. Or I can also do the same thing here with vector A. So put the head of vector A, the tail of vector A at the head of vector B. Okay, so this is also A. And then basically, if I draw then a line from the tail, or where these both meet, to this intersection point, and that should be a straight line. So this is my vector A plus B. Okay, so that's how I add vectors, is basically this head to tail method like this. Okay, so once again, what I did is, as I said, a vector has to have a vectors are equal if they have the same magnitude and direction. So as long as I don't change the magnitude and direction of B or A, as long as I keep the same length and point in the same direction, I can move it around. So I just move it in a convenient way where the head of the tail of vector B is at the head of vector A. And I draw a line from that point, from where A was, to this new point where the head of B is. And that gives me the magnitude and direction of vector A plus B. Now, how I find that magnitude and direction, if I know the magnitude and direction of vectors A and B, then I can find that using trigonometry, such as the law of sines or law of cosines, depending on what you know. Okay, so that's A plus B. Now, what if we had A minus B? So vector A minus B, well, it turns out, just like regular math, that's the same as vector A plus a negative B. Okay, and as we saw, let's make a little bit bigger picture. I should have made this bigger to begin with. So here is vector, here's vector B, and here is vector A. Okay, so as we saw earlier, to make a negative B, I just have a vector the same length as B pointing in the opposite direction. And so that should look like this. This is negative B. Okay, now do the same thing. Okay, in this case, I think I'll move vector A, so the tail of vector A to the head of vector B. And basically, I'm making a parallelogram. Of course, this would be vector minus B up here. My A, well, actually, well, let me move my A out of the way. So this is A. Okay, and do this either way. This is negative B, of course. This is A. And then once again, this line right here that goes from this intersection point to where those two vectors meet, okay, or the head of, or actually where the head of vector, in this case, vector A and vector B meet, is going to be A minus B. Okay, so that's graphically how we do that. And then we'll have to talk about actually then finding those values. Okay, let's see what else I need to mention. That's what I mentioned here. So vectors, then also adding, subtracting. Okay, let me say one more thing about vectors. Let's say once again we have vectors A and B. So let's talk about what's called the magnitude and direction. I mentioned that. Let's define it a bit more. Okay, so the magnitude of some vector A is usually written with essentially absolute value signs like that. Okay, to have some vector A, that's its magnitude. All right. So if I also have the magnitude of B, I'll screw with this. The magnitude of vector B in the same way is just going to be written with absolute value signs around vector B. Okay. Now, we're talking about the direction. We can do that a couple different ways. So, for example, if I have a coordinate system here, okay, where if this is, X and Y, then my direction could be, for example, this is my vector A. The angle theta is my direction. And that could be from, for example, like a positive x-axis, or it could be some other axis. Okay, that can be one way direction. All right, or so that's kind of an absolute direction. Or we can also have, once again, if this is vector A and this is vector B, And this theta right here would essentially be the essentially a relative direction. So the relative direction between those vectors. Okay. And often that's what's really important to know is the relative vector, the relative direction between two vectors. Okay. So let's look at a few examples now that we've seen this, working with these ideas. Okay, so let's say number one, we have two forces of 19 newtons. So a newton is a unit of force. Okay. And also plus 32 newtons. Okay. And the basically they form an angle, or the angle between them of 118 degrees. Okay. We want to let's find the magnitude and the direction of the resultant force. Okay, so let's draw a picture of this. So we have two forces. You want to call them A and B, you can. So basically this is, I may do that anyway. So A, let's call this force A, and the magnitude of A is 19 newtons, let's say pointing this direction. And the angle between them, and this is quite a bit longer. And so this is B, and the magnitude of angle B, we said, is 32 newtons. So in terms of forces. So once again, where to expect our force, or if we're thinking about pushing something right here, expect kind of go somewhere in this direction. Okay. And this angle in between them then is going to be, this theta is equal to 118 degrees. Make that better. 118 degrees between them. Okay. So now if we do our same thing, put our vectors head to tail, as we mentioned. Make a parallelogram. Once again, this is A, this is B. Then our vector A plus B, so this is called the resultant. The resultant force is A plus B. Okay, well, let's think about that. So basically what we have now, let's back up a bit and take a look at this. So let's take a look at, we can't give you either one of these triangles. And I may just use this one right here. So let's take either this triangle or this triangle and redraw it. And so we have this. Okay, so this is one that was 32 newtons. This was 19 newtons. Okay, and this is our resultant force. So and actually we're looking for, let's call this F to make it easier. Okay, and so we're looking for then this length here is actually then the magnitude of our force F. Okay, now let's also add a few more things here. So we said this angle right here was 118 degrees. Okay, because what we need to do then to find this angle, we also need at least another angle here of the triangle. We don't know what this angle is, But actually, we can find this one, because what happens then if we extend this on in this direction, okay, then this angle right here, this little geometry here, is a supplementary angle of this one. So if that makes sense. So if I draw these with this, so these directions both go in the same direction here. Okay. This angle here is 118 degrees. And so this angle here is also 118 degrees. Okay. So what I can do then is just subtract 180 minus 818. And this angle then is going to be 62 degrees. Okay, good. So how does that help us? Well, what I can do is I can use the law of cosines. Okay, so the law of cosines, basically, this is, if you remember, if you've seen my previous video on the law of cosines or know about the law of cosines, this is basically the side angle side case with the two sides, the angle in between them. That's where you use the law of cosines. What that says, the magnitude of f, okay, this length, is equal to the sum of the squares of the other two sides. So 19 squared plus 32 squared minus 2 times 19, that side, times 32 times, I'm sorry, I need more space. Let me start that over here again. That's a little bit smaller. So the magnitude of f, and actually that's going to be the square root of all that, because this is actually that squared, okay, is going to be, so 19 squared plus 32 squared minus 2 times 19 times 32 times the cosine of 62. Okay, the cosine of that angle. All right. Now, I did it that way because actually let's go to Desmos and plug all that in one step. Okay, that's the best way to do this. So, all right. So do a square root. You can either go down to the keyboard and square it right here, or you just type the letters SQRT. But so it's going to be 19 squared. Should be on the inside. So 19 squared plus 32 squared. And actually, I realize I need to make sure I'm in degree mode. Okay, so go over to the little wrench here and change to degrees. Otherwise, I'd be telling it 162 radians, which is very different. Okay. Then where we are here again, minus 2 times 19 times 32 times the cosine of 62 degrees. And what is that? Okay, so that length then is going to be, so let's say go 2 decimal places, so 28.53. Okay, about 28.53. And so that's the magnitude of our resultant force is, I forget what it was, 28.53 newtons. Okay, that's resultant force. So these two forces, one pushing this way and one pushing this direction, going in this, moving this direction, pushing this direction, the net result of those, adding them together, is moving that direction with that force. Okay. All right. So then we're able to find then what that is. Okay. Now let's also do one more thing. Let's find, what if we want to find the angle of the force with respect to, well, let me redraw our triangle again. So here's our triangle. Okay, so this was 32. So it's not exactly the scale. This is 28.53. These are all newtons. Now, what I mean is with respect to the dotted line. Okay, that's my original force, 19 force here. Okay, now, with respect to that, now we said this angle is 118 degrees. So what we're going to do then is find this little theta right here. Okay, this angle right here. Let's draw that again. So what we're looking for then is this one's 28.53. I want to find this theta. Okay, so how can we do that? Well, what we can do now is that now that we know all three sides of this triangle, what we can do is, now that you know all three sides, you can find any one of these angles. Okay, this is the side, side, side case for law of cosines. We use law of cosines again. All right, and what we do, let's find, let's call this angle right here, let's call this alpha. Okay, so let's first find angle alpha. I shouldn't say, so I want to find angle theta, but first let's find alpha. Okay, now we can do that. All right, what we're going to do is, we know the two sides, we know these two sides here. All right, and what we can do is we can take the law of cosines. What that's going to be, we actually solve it for the cosine of alpha. What we have is that the cosine of alpha is equal to the opposite side squared, which is 19 squared, minus 32 squared, minus 28.53 squared. This is all over minus 2 times 32 times 28.53. Okay, let's plug that in to Desmos. All right, so up here we had the 19 squared. And once again, where I'm getting that is from law of cosine. So if you've seen my previous video on the law of cosines, or you haven't seen it, make sure you go back and look at that. All right, so minus 32 squared minus 28.53 squared. Okay, then divided by minus 2 times 32 times 28.53. Okay, and what that gives us, as you can see, is, let's use about 5 places here, 0.8088, be 0.80889. .80889. Okay, then if we take the inverse cosine of both sides, this gives us then alpha is equal to the inverse cosine of 0.80889. Let's make sure you're in degree mode. Otherwise, you get an answer in radians. And make sure you have that in your calculator. So let's find alpha. And so let's do the inverse cosine of that. So to find the inverse cosine, click on the keyboard on Desmos, go to functions, and then inverse cosines right here. Oops, that's the wrong place. I'm sorry. Go down here and do that same thing. Then cosine of 0.80889, and that's approximately, as it says, approximately 36.01 degrees. Just use 2 decimal places. Of course, use whatever decimal places is required by the problem, but it doesn't say. So 36.01. Yes, so approximately 36.01 degrees. Okay, so let's take a look at our picture again. So I found that alpha is equal to 36.01. So my angle theta then, from the geometry here, let's take a look at our triangle. Okay, this whole angle from here to here is 118. Alpha, we said, is 36.01. So our theta is basically 118 minus alpha. minus 36.01, and I'll just use my calculator and calculator for that. And that's approximately, so theta is approximately 81.99 degrees. So approximately 82 degrees. Okay. So if we think of this as kind of think of this being like where this vector points is the kind of a horizontal thing is horizontal. We're making this vector is pointing then approximately about 82 degrees from the horizontal. Okay. So think of this as being like the x-axis and the y-axis running that way. Then that's basically 118 degrees from the horizontal. Okay. So what we've learned so far, we've learned today, is basically essentially the basics of vectors. And we looked at an application problem. So we learned the basic difference between vectors and scalars. Okay, so a scalar is a number you only be defined by one number, which is magnitude, like temperature, pressure, and so forth. Okay, a vector is something that has to be determined by two magnitudes, two things, a magnitude and a direction, such as a force or such as speed. Okay, and then we learned how to add and subtract vectors, and then also then how to actually then add subtract vectors, then actually define basically the magnitude of resultant vector and how to find the direction of that resultant vector from some direction. Okay, some direction has to be chosen. Okay, let's take a look at one more example. So number 2. Okay, and this is something that happens and kind of happens in real life. So imagine a plane, an airplane, flies. Let's make it simple. So due north at 100 miles per hour. Okay, then we have a wind that blows, let's say 20 miles per hour. Toward, let's see, what should I pick? Um, Toward 225 degrees. Okay. What I want to do then is find the resultant speed and direction of the airplane, of the plane. Okay, once again, let's draw a picture to make some sense of this. So, a good chance you may know this, but basically, in with planes and with ships, due north, okay, this is considered to be 0 degrees. Okay, then due east is 90 degrees. Due south is 180 degrees. And then due west is 270 degrees. So this is actually kind of backwards from what, not the same as when we do trigonometry. It's not really the same. Okay. There are 0 degrees is essentially along the x-axis. Here we're doing it this way. Okay. This is the way it's done in with ships and airplanes. It's traditionally done. Okay. So what we have then is our plane is basically flying this direction. And then again. In fact, let me just use a different color. Okay, so our plane is flying this direction. Okay, at 100 miles per hour. And that's the vector, it's direction and speed. That's the plane. Okay, essentially it's flying at that heading in that direction. Okay, but the wind is coming from, let's see what I think, so 225. Okay, 20 miles an hour, so 225 should be essentially right in the middle here of these two. and at 20 miles an hour. So this is that's the wind. So, and actually, once again, I realize I should have written this on the other side. So our resultant then so our plane, which is going 100 miles per hour, that heading, okay? The resultant then, once again, if I do this head to tail vector, I should make a parallelogram, okay? Then our resultant should look, well, let's make sure I can draw a straight line. Try that one more time. Is basically heading in this direction, okay? Now let's just call that V, okay? And that's the magnitude of V, so our vector V, okay? And that's a resultant. So vector V is the resultant, and then we want to find then the magnitude and also this direction with respect to due north, okay? Need to find this direction, well, we need to find this angle right here, okay? And that will tell us kind of what we need. So this is not actually the final angle, but we need to find that angle theta. Okay, so let's go down here and draw a picture of this triangle again. All right. So we have something like this. So this length is 100 miles per hour. Right. And then we said this one is basically 20 miles per hour going this direction. And this is our resultant vector V, its magnitude. I want to find that magnitude. And then we also want to find then, this angle theta. Okay. So in this case, we actually, so what do we know? Well, we know so we need to find this magnitude, and of course, this angle. Now, in this case, we don't know the angle in between, at least not yet. So we need to figure that out kind of from our geometry of our problem. Okay. So if we do that, and let's see, I probably need to move some things around again. Okay. So let's make a line right here, a horizontal line. What we're going to do, once again, I'll just put this right. So this is 20 miles per hour, that length. All right. Now, let's think about what happens. So here we said west, this is 270. This direction here is 225. Okay. So this angle between from essentially my x-axis here and this angle is 45 degrees. So if I draw a similar line across here, that angle is also going to be 45 degrees. Okay. So this is 45 degrees. And since it turns out that then this is also 45 degrees, 90 minus that. Okay. So now we have that angle in between them. Okay. So what I did is this direction is going 225. So essentially 270 minus 225 is 45. This angle here is 45 between these two. So if I draw a line parallel to my x-axis right through here, which is what I've done here. Okay. And this angle is 45. So these two angles together make up 90 degrees. They're complementary to each other. So 90 minus 45 is also 45. Okay. So let's find the length. So let's find the magnitude of our velocity vector. And so, once again, from the law of cosines, that's going to be square root of the sum of the squares of the other two sides. So 20 squared plus 100 squared and minus 2 times the other two sides, 20 times 100, then times the cosine of the angle in between them, which is 45. Okay. Well, let's do that on Desmos. You should use your graphing calculator also if you want. All right, so this looks just like this, what we did right here. So I'll also do a squared, type SQRT. All right, and so we have 20 squared plus 100 squared minus 2 times 20. Well, actually, I think I'll just use multiplication symbol. 2 times 20 times 100, then times the cosine, just type COS of 45. I'm still in degree mode. And so that length then is going to be 87. Let's do 2 places again. 87.01 miles per hour. 87.01 miles per hour. Okay, so that's the magnitude of my new vector. We'll explain what that means here in a minute. Okay, we found that. So now let's find that angle theta. Okay, well, so to do that, so I now know all 3 sides of my triangle. And so I can always use the law of cosines for this angle here. All right, and so if I solve this for cosine of theta, once again, theta is not my final angle. We'll talk about that in a moment, but cosine of theta is going to be, so it's going to be the opposite side, which is 20. That's just 20 squared minus the squares of the other 2 sides. So 100 minus 100 squared minus 87.01 squared. And this is all divided by minus 2 times these other 2 sides, 187.01. Okay, so let's plug all that into Desmos. Okay, so we've done a similar thing before. Parentheses, so 20 squared minus 100 squared minus 87.01 squared. Okay, then divided by, I need parentheses, make sure you're dividing by the whole thing, minus 2 times 100 times 87.01. And that's about let's use 5 places again, 0.98671. Okay, so 0.98671. Okay, and so if I take the inverse cosine of both sides, then that's going to give me theta is equal to, actually I need to check something because I maybe got out of, make sure I have enough virtual paper here to do everything. That should be more than enough. We're almost at the end. Okay, the theta is equal to the inverse cosine of that, 0.98671. All right, let's do that then. Desmos. So once again, the inverse cosine, hit the keyboard, hit functions, and the inverse trig functions. There's it. I did it again. Sorry. That should be on the next line. Down here. And inverse cosine of 0.98671. Also, the more these decimal places used, the more accurate that will be. And so that turns out that theta then is, once again, 2 places, about 9.35 degrees, which is a fairly small angle. Now, I said that's not quite our final answer because although that is that angle in our triangle, 9.35 degrees, basically, since you want to know what direction that is. Okay. So let's go back and take a look at that. So let's draw another picture. And so essentially our new magnitude and direction. All right, so once again, this is north. Once again, this is 0 degrees. East, which is 90 degrees. South, which is 180 degrees. And then west, which is 270. Now, Probably the easy way to do this on the new magnitude direction looks like this. So this was 87.01 miles per hour. And then this, we said this theta is equal to 9.35 degrees. So the easiest way to find my direction essentially my compass direction, compass heading. The easiest way to do that is now you could also, if we knew this angle right here, okay, which we can find, okay. So this one's going to go back and take a quick look. That original picture. Okay, I found this theta. Okay, now if we find this angle with the x-axis, a couple ways we can do this. Let's find this angle with west. Okay, so this angle, let's call that angle alpha. Okay, and so theta and alpha together make 90 degrees. And so alpha is going to be 90 minus 9.35 degrees. And that's going to be 80.65. Okay, and then the final thing then, so our heading is just going to be west, which is 270, okay, plus alpha. 270 plus 80.65 degrees. And so that's going to be 350.65 degrees, or basically 351 degrees. So that's the heading. Okay. Now we could have also gotten that because if you think about going all the way around, 0 degrees is the same as 360 degrees. So we could have just subtracted from 360 and got the same thing. Okay. Now let's mention one more thing, explain how this kind of how, especially an aircraft, how an airplane this works. So based on an airplane, it's on the airplane, your heading, what you're reading on the compass, would actually be 0 degrees. Okay, you're heading due north and going 100 miles an hour. That 100 miles an hour, though, is relative, it's basically relative to the air you're in, the air you're in. But the wind, the air you're in, then is actually moving 20 miles per hour in this direction. Okay, so your resulting vector, as we saw then, the resulting heading, you're actually going only about 87 miles an hour. So because the wind is kind of going against you, then you're going more slowly than you think. Okay, in terms of what's called the ground speed, that's how fast you're going as moving to the ground. So relative to the wind, you're going 100 miles an hour. Relative to the ground, you're actually going slower than that. You're actually going in a direction about 10 degrees on this way. So pilots and also people in flying ships also have to do this, or working with ships also have to do the same thing. They have to correct for wind. They have to make sure they understand what's called their ground speed, how fast they're actually going across the ground, and actually their true heading based on essentially taking the wind into effect, then to make sure they get to their destination correctly. Because, after several miles of that kind of direction, if you think you're actually going 0 degrees true north, you're actually going, you know, 10 degrees off that, then after a few hours, you can be pretty far off course. So they have to take all that into account in flying and also in sailing and working on ships. Okay, so to review, what we've done is learn the basics of vectors. We've learned the difference between scalars and vectors, learned about graphing vectors based on magnitudes and directions, vectors that are equal and not equal, and also learned how to add and subtract vectors graphically, then also how to find the resultant magnitudes of vectors, and then also how to find their directions. Thank you. Have a good night.